Before diving into specific mechanisms, let's establish the foundational concepts of radical chemistry. Unlike ionic reactions, which involve the movement of electron pairs, radical reactions are driven by the movement of single, unpaired electrons. To represent this single electron movement, we use single-barbed curved arrows, commonly known as fishhook arrows. While a standard curved arrow with a full arrowhead represents the movement of an electron pair, a fishhook arrow explicitly indicates the movement of just one single electron. So, what exactly is a radical? A radical, or free radical, is a chemical species containing one or more unpaired electrons. To understand its electronic nature, let's compare a carbon radical with familiar ionic intermediates. A carbocation ion has 6 valence electrons, carries a positive charge, and adopts an sp2 hybridization with a trigonal planar geometry. A carbon ion has 8 valence electrons, including a lone pair, carries a negative charge, and adopts an sp3 hybridization with a trigonal pyramidal geometry. A carbon radical, on the other hand, possesses 7 valence electrons and is also sp2 hybridized. Because it has 7 electrons, it is electrically neutral, yet highly reactive due to its incomplete octet and unpaired electron residing in an unhybridized p orbital. This difference in electron count stems directly from how chemical bonds break. In heterolytic cleavage, a covalent bond breaks unsymmetrically. One atom takes both bonding electrons, forming an anion and a cation. In homolytic cleavage, the bond cleaves symmetrically. Each atom takes one electron, generating 2 neutral radical species. Now, let's examine the geometry and electronic configuration of a carbon radical. A simple alkyl radical is sp2 hybridized, adopting a trigonal planar geometry with bond angles of approximately 120 degrees. The 3 sp2 hybrid orbitals form sigma bonds with surrounding atoms, while the single unpaired electron resides in the unhybridized p orbital, perpendicular to the molecular plane. This planar symmetry and the presence of the unpaired electron in the p orbital are crucial, as they directly dictate the stereochemical outcomes of radical reactions. Finally, it's worth noting that non-carbon radicals display different structural and hybridization characteristics. Oxygen radicals, such as alkoxy radicals, feature an sp3 hybridized oxygen atom that retains 2 lone pairs alongside a single unpaired electron in one of its sp3 hybrid orbitals. Halogen radicals, such as chlorine or bromine atoms, carry 7 valence electrons in their outer shell, 3 lone pairs, and 1 unpaired electron in their unhybridized atomic orbitals, giving them a spherical atomic symmetry. Building on what we've discussed about the fundamentals and structure of radicals, let's now look at how these reactive species are generated. Because radicals are high-energy, unstable species, they cannot simply form on their own under standard conditions. They require a specific trigger, a substance known as a radical initiator. An initiator is a compound containing a relatively weak covalent bond that easily undergoes homolytic cleavage upon exposure to heat or light. The most common initiators are peroxides and halogens. When light energy or thermal energy is absorbed, the weak single bond between the oxygen atoms or halogen atoms breaks symmetrically. Using fishhook arrows, we show 1 electron moving to each atom, yielding 2 identical radical species. Why do these specific bonds break so easily? It all comes down to bond dissociation energy, or BDE. Standard covalent bonds like CH or CC have high bond dissociation energies, making homolytic cleavage thermally unfavorable. However, in peroxides, the central OO single bond has a remarkably low BDE, roughly 150 kilojoules per mole, due to severe lone pair repulsion between the adjacent oxygen atoms. Halogen bonds similarly exhibit low BDEs, allowing light or mild heating to trigger homolytic cleavage effortlessly. So, how are these essential peroxide compounds formed in the first place? They can be generated through the autoxidation of organic compounds, such as ethers. When a substrate reacts with atmospheric triplet oxygen, which naturally exists as a diradical, a hydrogen atom is abstracted from a relatively weak CH bond, such as the alpha CH bond in an ether, forming a carbon radical. This radical rapidly combines with oxygen to form a peroxy radical, which then abstracts another hydrogen atom from a neighboring molecule to yield a hydroperoxide. Under heat or light, the weak OO bond of these hydroperoxides can undergo homolytic cleavage, generating radicals that can initiate or propagate radical chain processes. Most radical processes operate through a chain reaction framework, a continuous sequence where a few initial radicals transform a large amount of starting materials. Regardless of the specific reaction, most radical chain mechanisms follow three general steps: initiation, propagation, and termination. And first is initiation. Here, initiator molecules undergo homolytic cleavage, often triggered by light or heat, generating the initial radicals needed to start the reaction. Second is propagation, the core of the chain reaction. A radical reacts with a stable molecule to form a product while regenerating a new radical. This creates a self-sustaining cycle that repeats thousands of times. Finally, termination. When radicals react with one another, they are consumed without generating a new radical, bringing the chain reaction to a halt. Mastering this three-step framework gives you the template to analyze any radical reaction in organic chemistry.